impressed with your, perseverance so far. Yes, so Matteo, would you like to find a friend? Zijie, we see your screen. It's lovely.
Yeah.
Yeah, we're very happy that you fixed it
Right.
real time. But
I
we'll
have
continue
here-
this introduction. I'll let Zijie take over, but
Yes.
I'm
Okay.
still listening.
Great. I just fixed. Sorry about the technical issue because this is a new computer, so it take me some time to fix it. Yeah. So great. I think now we can start it. So if you haven't introduced yourself, we can do later on. So hi everyone. So welcome to the recitation, the first recitation session for the fundamentals of statistics course. I'm very happy to see you guys come here today. So let's get started. Can everyone see the screen now? Okay, perfect. Okay. So first, I want to ask you a question: why you are here, right? I can see I am here because I'm super excited about statistics. So we are going to learn the basic statistics in this course, and I hope you guys can learn a lot about statistics, because statistics is a very fancy thing. Okay. So then I wanted to talk about the course goals and the overview of this course. So first, I would say that it's a mathematical course. So it would be a fair amount of notation, but you will find that it could be really helpful. And for this course, we will also learn the way that the statistician think about the data, and you will develop your own statistics toolkit for your future research or your future career path. And at the end, you will get a statistics and data science job, right? Sounds really cool. Okay. So I will introduce myself again. I'm Zijie, the first year PhD at MIT ECS, which stands for the Electrical Engineering and Computer Science. And previously, I'm a master's student at Harvard in biostatistics. Now my current research is on applied machine learning. So I used to be a previous MicroMaster certifications holder. 2 years ago, I was a student as well, like you, to learn about these courses. So I know you will be having many problems. So feel free to ask me if you have any problems for this questions for this course, and I will be your primary TA this term. Okay, and I really hope everyone can succeed in this course, right? There is a tips can help you. That is work hard, work smart, and ask for help. And I'm always here to help you. So one thing to mention is that feel free to interrupt me. You can just raise your hand in the Zoom, or just unmute yourself and asking question. It's totally fine. Yeah, it's really fine to just interrupt me. Yeah. Okay. Another thing to notice that if you type your question in the Zoom chat, because I'm watching the slides, I may not notice in time. So if you have a quick question, so just unmute yourself and ask. So I will answer your question in the recitation session. Okay, so today's recitation agenda is the first is review some concepts, which is maybe from your lecture or the prerequisite, like the probability courses. And then we will do some exercise, that is read the problems and think think the problems by yourself, and then I will send you to some breakout room for discussion. And finally, I will lead you guys to walking through the question. Okay, so the learning outcome for today's session is by the end of this recitation, you need to know the definition of random variables and the distribution. You should know for your probability courses, but today we will review these definitions as well. And also you should know and apply the law of large numbers and the central limit theorem. Okay, so I know some guys have already introduced yourself. So have anyone haven't introduced yourself in just 1 or 2 minutes? Have anyone doesn't introduce yourself?
Yes, my name is Nicholas and I am a computer analyst. I did this probability and machine learning, and I found more challenging for me the probability course. The machine learning course, I like it very much, but I agree there is the time is too short, and especially I would like to do some tests of the real data, and I didn't have the chance to do it, but I like it very much.
Yeah. Nice to see you for this course. Next one. Yeah, you can just have a very quick introduction for yourself to let us know your name and your interest for this course.
Well, my name is Ines. I am biologist, and I agree with the opinion about the courses. I like it very much, probability, and I like machine learning. It was very difficult. But well, I think that if I have the possibility to have the course of machine learning, I will do better. But I like it, and I suppose that this course I would like to.
Sounds great. Yeah, machine learning is a fancy stuff.
It's very different, and
yeah,
comparing with others, and I think it's difficult.
Next one.
My name is Edison Arcos. I am from Ecuador. I am mechanical engineer. I returned to study maybe 15 years, but for me it's nice to course, because in the probabilities for me was a difficult, but it's interesting return to review some topics that are studied in the last years of my university. Machine learning is nice course. It's nice. For me, it's very difficult to script and writing code, but it's nice. Maybe I take the words of Ines. I would like to review another course because the time is short for this topic. Nice.
Cool. Yeah. What about next one? Okay. It seems like everyone already get introduced yourself, right? Yeah, just double check. If you haven't introduced yourself, just feel free to unmute yourself at this time. I just wait like another 20 seconds and I will go to the next activity. Okay, great. I think everyone get introduced yourself, and Yeah, I think it's cool to see you guys have a big interest in statistics, data science, and also machine learning. And you guys know that this course, the fundamental of statistics, is a very important fundamentals courses for machine learning. So if you guys really interested in like statistics and data science jobs, this course is really, really important. And you will find that the content you learn in this course will be really useful for your future career path. Okay, so then we will go to the next slide. So the next part for this recitation is I will lead you to review some concepts. You maybe learn from your previous lecture, but I will just make sure that everyone get review at this time again. So let's refresh your probability knowledge. Okay, so the first definition is what we call the probability distribution. Actually, it is a non-negative weighting on a set of an outcome or events, and the weights should be add to 1. So maybe we can, for an example, that is the Bernoulli distribution. Does anyone have a know the Bernoulli? Let me ask some question. Okay, can Edison answer Edison, right? Is I spelling right? Can you answer this question?
Repeat the answer, the question.
Yeah. I can hear. Yeah. Do you know what is the Bernoulli distribution? Have you learned it? Or yeah, it's okay. It's totally fine if you don't know that.
The
What is it?
Bernoulli is the probability that is probability maybe type 1 or type value 1 or 0, right?
Yeah. Yes. Perfect. Yeah. Yeah. Okay. It's fine. Yeah.
For one probability P, for other, I don't remember.
Yeah. It's totally fine. Yeah, we would like let you to review this concept. Okay, so I will go deep for the definition of what is called the Bernoulli. Okay, the Bernoulli is a very common distribution you will find in both in statistics and especially in this course you will find all of the examples are there are Bernoulli distribution. So what is the Bernoulli distribution? It's like it's like a Boole variables in computer science. Like there are only 2 possible values, 0 or 1, right? But maybe you because you know random variable, there is a lot uncertainty for it. So maybe sometime it should be 1 or other time it should be 0. So there would be some probability associated with it. So for example, the Bernoulli, when it's the parameters for Bernoulli distribution is we call P, right? So if Bernoulli P equals to 0.2, which means that there is a 0.2 probability that the X should be 1. And the rest of the time which means the probability equals to 0.8 that the random variable X should be 1. You only have a 2 choice, 0 or 1. And you will see a concrete example for Bernoulli distribution later on. But I will just give you a quick example is that Bernoulli distribution is like when you toss a coin, it should be head or tail, right? So you can like think about there is you can only have 2 values, 0 or 1. Okay, next. The sample space. Okay, the sample space is very simple. That is just a set of outcomes of a distribution, like all of the possible outcome for a distribution. For Bernoulli, the sample space is just a set of 0 or 1, right? But here is a definition that is but here you can see that there is a 1, 2, 3, 4. The combination of 1, 2, 3, 4. These sets should be another sample space, right? Also, you will have another other set, like this one should be also the sample space, right? You can just think of all the possible values that random variable could be, and those combination for those possible values should be a sample space. What is the random variable? The random variable is that the quantity given by sampling from the distribution. So the random variables would take that values in the sample space. Okay, so for example, when X is a sample space, so it should take from this sample space, right? It should take value. So it should be 1 at some times, or it should be equal to 2 at another times, right? So the X we call is random variables. Okay, so the next definition is what we call expectation. So you may learn this stuff in your probability course, but I will review it again. So the expectation is, it seems like you take an average, right? So the expectation is when you have the value itself and its probability, you just multiply those two stuff and integrate all the possible values. So for example, so the X, you have a 1, 2, 3, 4, and its probability, for example, it's difficult to write. Maybe you have a 0.2, 0.2, 0, 0.5, 0.5, right? You have a 1/4 probability for each of the value. And then you should multiply those two stuff and integrate it. That is called the expectation. So you compute as 1, apply its 1/4, its probability, and you add 2 times its associated probability, and you do this stuff. That is called the expectation. Okay. So if you have any question, just feel free to unmute yourself and asking question, or type your question in the chat box. Okay, so the next definition we will review is we call the independence. So intuitively, if we call the X, Y, they are both random variables, are independent. So which means that the X and Y don't affect each other. So how do we think about mathematically? So in math, we call when X and Y are independent, we are think about, the statistician think about in this way. That is the probability that X equals to K and Y equals to J is multiplied by the PX and the PY. So which means that it is a PXY is just the multiplication for the PX and the PY, which means that you can see that at these times, the X and Y, right, they don't affect each other. They just, there is an independence between the random variable X and Y. So this is the definition for the independence. Okay. So then we will go over a really important theory. You should be usually you should be applied so many times in this course, I think, both for your exercise or your exam. So it's very important theory. We call it a law of large numbers. Okay, it's fine if you haven't reviewed this. If you don't remember this theory, it's totally fine. We will go through it today. Okay, what is we call the law of large numbers? The law of large numbers means that the X is a random variable, right? If have some fancy or strange or normal or balloony, like, right? You have a binomial distribution or any distribution you like with a mu, right? Mu is expectation. And then we will have, if we have a random sample that is sample from that distribution, we just take the sample mean. The sample mean is you just take the average. You add all those stuff and take the average. That should be approach to its true mean. So this theorem is intuitively, this theorem is very simple. You just sample from a distribution and you sample it so many times, like 100, 1,000, 1 million times, and you get a lots of sample, right? And you just take the average from those two samples. That should be approach to the true mean if you sample it more and more times. The more sample you get, the prices result you should get. Okay, so that is the basic idea for this. So we can I can go through a concrete example for you, just like the toast coins, right? So for the toast coin, you have if we let the random variables to be the x, so x should have two possible values, which is 0 or 1, right? So maybe the 0 is represent you toss the coin to be the tail, and the 1 that is toss the coin to be the head. So you only have two possible values. That is we call the Bernoulli distribution, right? So the Bernoulli distribution, you would have a parameters called the p, which is the successful rate. The successful probability, successful rate you should think about, that is the proportion of times that you toss a coin to be the head, right? So for example, when p is equal to 0.2, which means that there is a 20% proportion that you toss a coin to be the 1, and the rest of the proportion you toss to be the tail. Okay, so when you toss it so many times, like here is a 5 flips, 10 flips, or 20 flips, and you just count, right? Count the proportion of the heads, right? If you toss like 1 times, it should be no head, right? It should be just tail. When you toss second time, it should be also the tail, right? Because it's a random variable. If you toss third time, it should be also tail. But if you toss a coin more and more times, right, you would have some heads. And if you toss like maybe 20 times in this example, or you just toss it 100 times, so you know that if the coins are fair, there should be the p should be equal to 1/2, right? Because if the coins are fair, you should have the 50% possibility that the coins should be either tail or head. So this is just a law of a large number. You see that if you toss it more and more times, you should be really converge to its theoretical probability. So the white dots on the image is the sample. It's an estimate for this p, right? But if you try more and more times, it should be really close to its theoretical value. So this is the basic idea. Okay, so let me do a very quick exercise. So I think it's very simple because I just go over this example just now. That is a coin flips, right? So let the Q denoted the probability that the coin flips to be the head. And you observe that the X to be either 0 or 1. So the 1 means head and 0 means tail. So could you write down the quantity in terms of the observations that could gives a good approximation for Q, assuming that when the N is a very large. So think about the way that to estimate what is the value of the Q, right? So now I will send you guys to several breakout Zoom, and you will have a time to to first think about yourself, right? And then discuss with your peer to come up a solution that you think that is a good approximation for this Q. So this Q means that the probability that the coins flips hat. Okay, so now I will send you guys to the breakout Zooms. If you have any questions, just, yeah, feel free to interrupt me. Okay, have you guys, I think you should be, I received the message to enjoy the rooms.
O sea, son los X dividido los N y ya está, la
Y
sumatoria.
sí,
Hello,
y bueno,
have you guys
Hello,
have some
how are you?
idea for this question?
hello.
Hello.
We were saying that is the summatory of all X divided by M.
Oh, yes, yes, perfect. Yeah. Okay, I will switch to another breakout Zoom to make sure, and we will go through the solution again. Yeah. Okay, perfect. Good job.
Okay,
Yeah.
bye.
Bye.
Nicola, you finished.
Is things going well for this question? Yeah, I think most of you are get the correct answer. Yeah. So okay. Can you guys see the screen?
No.
Oh, okay.
Oh, no.
I see your face.
Oh, okay. I will share my screen again. Okay, I will give you a solution. So actually this solution is very simple. You just take the sum of all the possible value and divide it by n, right? This is a very intuitive solution, but why this happened, right? Why you have got this solution? So we can see that actually this is, we called the sample mean, right? You just sum up all the random variable x, all the samples you get, and divide it by the n, right? You just take the average. So this means the sample mean. So why it should converge to the true mean? So actually, when you have a Bernoulli distribution P, you can convince yourself that the expectation should be the P. So that means the sample mean is converged to the true mean. But why this happened? This is called the law of large number. It's due to the law of large numbers. And you will find and apply the law of large numbers so many times in our class. Why? Because you only have a sample, right? In the real life, you only have a sample. You don't have you don't access to the true distribution. And if you want to estimate the distribution, like the parameter of that distribution, like the P, you should use the sample you get from that distribution and approach to the true mean. So at that time, you should apply the law of large number. So this is the case for the Bernoulli distribution, but the idea should apply to other distribution like the binomial distribution, or like the normal distribution, or some fancy distribution like beta distribution, gamma distribution, negative binomial distribution. The basic idea is the same, right? So you get the sample mean and you use it to approach the true mean. That is a basic idea. And the idea behind this is you apply the law of large numbers. Okay, so then we will move on to next really, really important concept, which is called the central limit theorem. It's totally fine. You don't know this theorem. We will I will find some intuitive way to help you to learn this theorem if you don't have any idea. But I expect you should learn from your probability courses. Okay, so this theorem is a little bit tricky than the previous theorem, that is the law of large numbers. So I will use some intuition to help you to review this theorem. So here, the black line, oh, sorry, I shouldn't use a red pen. So this line is like, is what, this distribution means that what we call the uniform distribution, that is the P, is an equal possibility that you could sample from the distribution. So for example, it should be 1, 2, 3, 4, 5, and the probability you assign to or you sample from this distribution should be equal, right? This is called the uniform distribution. The probability is uniform. So then you sample like maybe 10 points or 10 sample or 20 sample from this distribution, and you will calculate its means, right? For example, at this time, the mean should be 0.52. This is the, you don't have access to this distribution, but you can sample from it. So at this time, you sample like the 20 green dots and you calculate the mean. So the mean is equal to 0.58. So this vertical line represent you, the mean should be the 0.52 at this time. But you can do so many times, right? You can do 40 means. So for example, this times you get 0.39 for this time. And the second time, maybe you just exactly get 0.5. And at that time, yeah, you are less lucky and you get like maybe 0.6. But you can do so many times, right? Each time you calculate the mean, and this time you have a 40 means. So then when you plot a histogram for this 40 means, you have this shape, right? So you can find that its mean is really close to 0.5. And you also have some other means, maybe you are less lucky, you get a very strange means that is maybe close to 0.3, or you get 0.6, but you can plot that histogram, right? Okay, so when you try so many times, like 100 times, and you get a lot of means, each time you sample 20 dots and you calculate the mean, each time you calculate the mean, right? So here you have a 100 means. So you also plot the histogram of it. And when you try more and more times, you should find that the histogram is, you are converged, like you have a bell shape. That is the normal distribution. So when you plot the histogram, you're looking at the shape, you should find that the shape is more converged to what looks like a normal distribution. It's a little bit fancy and excited, right? So this is a normal distribution, right? But if you sample dots from it, right? You random sample the dots and take the mean, and you plot each means on the histogram, and you find that, whoa, the distribution of the mean, right? This is not the distribution of these dots. This is when you calculate the dots, when you sample the dots, you calculate the mean. And this is the distribution of the mean. The distribution of the mean is really look like a normal distribution when you try more and more times, right? So the bell shape will be a little bit tighter. If you try like only 20 times, the bell shape look like this, right? Or it's don't look like a bell shape, right? It's have a weird shape. But if you try so many times, like 100, 1,000 times, it should be like a perfect bell shape. So
one question, please.
Yeah, sure.
If you just sample the dots without calculating the mean, but in overall it's the same number of dots, you would end up with the same distribution or not?
Oh, okay. So I think you wouldn't get the normal distribution, right? So for example, if you have a uniform distribution, right, you just sample any dots from it, and you just plot the histogram of these dots, not its mean. So after you try so many times, it should be equals to a uniform distribution, right? Because you sample from this distribution. So if you have an exponential distribution and you sample 1,000 dots, and you should get the exponential distribution. It's not like the normal distribution. This is not the histogram of these dots. It's the histogram of its mean, right? The sample mean. Is that clarify your question?
Sorry, I lost my internet while you were answering.
Yeah, I will spell it again. So if you have a uniform distribution and you sample from it, you will get approximated uniform distribution. If you have an exponential distribution, you sample dots from it and you just plot a histogram of that dots, that value, right? You will have a approximate exponential distribution, right? Because you sample from a random distribution. If you sample it more and more times, it should be closer to the original distribution. It's not the case in these slides, because this is we calculate the mean. It's not the distribution for the dots. It's the distribution for the mean of the dots. Is that clarified? Yeah. So here we don't talk about the distribution of the random variable. We talk about the distribution of the mean of the random variable. Okay, we talk the sample mean. So sample means distribution. You can see here, I say the means distribution, not the values distribution, right?
Yeah, I understand what you said. I was just trying to understand if it's the same, you get the same result. You're saying no.
Okay. Oh, yeah. So, but you can see that so for the means distribution, if you have a fancy distribution like exponential distribution, and you also sample the dot here, you calculate the mean. You sample the second times, you get these dots, you calculate the mean, and you also plot the histogram of the mean. You should get a normal distribution. You also should get a normal distribution. Yes. Yeah. And you can try even like a more fancier distribution, like beta distribution, right? When you have this one, looks like a beta distribution, and you also sample the dots and you calculate the mean, right? Get one mean. You sample second times, you get another mean like here. You third times you get mean like here. So when you have so many means and you plot a histogram, right? You will find that the mean at here is the most case. The most case you get mean here, and less lucky you get means like this region or this region. But it should like a bell shape. It's a normal distribution. This is the intuition, right? This is the intuition. Okay, so here I will go through how do you calculate the sample mean and the sample variance. So here is just a mathematical form, right? I will go through line by line. So if you have any questions, just feel free to ask. So this is the expectation of the mean, right? The expectation of the mean, the sample mean. The sample mean's definition is this, right? So for the linearity of the expectation, you can just put out the one of the n to the outside, right? And here you just put the expectation of A plus B is the expectation of A plus expectation of the B, right? So I means E expectation of X and Y. X or Y, it's fine if it's dependence. It's fine. X and Y should be any random variable. This is called the linearity of the expectation. It should be equal to the EX plus EY, E of Y. Okay, this is called the linearity of expectation. And here, this is the mu, right? Because the expectation of a one sample should be equal to the mu. This is the true mean. This is also the true mean. And you calculate, you will get the mu. The mu is actually the true mean, right? This is the sample mean. This is the true mean. So we can get the sample mean is approach to its true mean. And what about the sample variance? You may know the variance, the definition of variance, but what is the sample's variance? The sample variance means that the variance of the mean, right? The variance of the mean. So why we care about the variance of the mean at this time? Because if we have a normal distribution, how tight is the distribution, right? If less variance, it should be tight. if it's large variance, it should be like a fat bell shape, right? So if the variance is a small, it have a fat bell shape. If the variance is big, you have a very tight bell shape. So that is why we care about the variance, right? So we already approved that the sample mean is the closest to the true mean. But what about the sample variance? So we also write down the variance like this way. And if you learn from the probability course, the variance of AX, right? When you plug this outside, you should just you should take the square, right, for the variance. But for the means, you shouldn't, right? For the variance, you just take the you get the 1 of the n square, right? So here is the variance of x to the n, and we know that at this time the independence is really important. But for this time, I don't mention this line, right? Because for the linearity of expectation, we don't care about it's dependent or not. But for when you calculate the variance, dependence is really important, because the variance, sorry. Yeah, for the next week, I will use the iPad. So there is a much easier to write down the formula, because for the variance of A plus B, you have the variance A, variance B.
You have an option to write it down in Zoom here too. In the notations tools, you can use a text box.
Oh, yes. That is a great idea. Yeah. So I mean, when you have an expectation A plus B, it should be equals to A expectation A of B, right? But the variance is different. You should care about the covariance, which I mean it's to covariance like the A and B. So that means the independence is really important, right? If the AB is important, this one should be equal to 0, and you should have those stuff, right? And so for the so the variance of the x1 is equal to sigma square. This is the true variance. And when you compute this value, you will get the sigma square divided by n. So here we would say that here is a you should divide it by n, right? But for the mean, the sample means, the expectation of the sample mean, you shouldn't divide it by n. But at this time, you must notice that you divide it by n in this case. Okay, so let's continue. Okay, so so we talk a lot. Yeah.
That was okay, but I was saying that the Zoom program has the tool to use it, like annotations, but with a textbooks. The Zoom program have the option in the bar at the top of the Zoom.
Oh,
it's okay. Don't worry.
Oh, okay. Yeah. We were talking about this tool at the end of the session. Okay. Okay. So we talk a lot about the central limit theorem before we talk about its mathematically, right? So we have a fancy distribution, and we take the sample mean, and the sample means distribution should look like a Gaussian, right? As we proved in the previous slides, its mean is equal to the true mean, and the variance is equal to the sigma square divided by n, and you take the square root of it. This is we call the standard deviation, right? It looks like a Gaussian. Okay, so why it looks like a Gaussian? We prove here, right? We do intuitively, it look like a Gaussian. You can try it. and why its expectation of it is equal to mu, and why its variance is equal to sigma divided by n. We prove that in these slides. And if you have any question, you can just refer to this formula to help you to think why the variance of its mean, the sample mean, is equal to sigma square. Sigma square is a true variance divided by n. So that's reason why I think why I said if you try, so the n gets bigger, the variance should be much smaller, right? So when the n increase, the variance of a x bar decrease. So that is why I said if you try 100 times, you get the bell shape like this. But if you tried 1 million times, you should have a much tighter bell shape, because which means that you are pretty much more confident when you try 1 million times, right? So the variance should be smaller because the n decrease. Okay, so here we talk about the central limit theorem. So the central limit theorem is if the x is a random variable from a population with mu mean and the finite variance sigma square, but the distribution can be fancy, can be strange, and it can be unknown, right? I don't say it should be a uniform distribution. I don't say it should be a normal distribution. It could be any distribution you like this, right? You should be any fancy, right? So which means central limit theorem is really cool because you can convert a strange or unknown population to a Gaussian distribution. I think everyone knows the Gaussian distribution, right? So it's a really cool technique to convert any strange distribution to a Gaussian, to a bell-shaped like distribution. So this series really makes the Gaussian distribution to the central of the statistics. So here we means the central, right? And the limit means approach. So we approach to a Gaussian. So this theorem is called central limit theorem. And you can find that in this course, you would apply it again and again. So it's really, really important. I think this is the most important theorem in the statistics. And you should definitely learn about this theorem. Okay, so here I talk about the formula to help you for a deep understanding. So we have already proved that the sample mean of it, right? I don't say the x is distributed by blah blah. I say the sample mean of x is a follow by a normal distribution, which the mean is the mu and the variance is sigma squared divided by n, right? I approve that in the previous slides. So if we minus the mu, right? If we shift the distribution to the mu unit, so we will get it's distributed at the center, at the point 0, right? This is very very clear. And if you also divide it by the you can think about this way, right? Here is a sigma square divided by square root of n, and you remove to the to this place, right? Yeah, and if you divide it by this is we call the standard error. If you divide it by the standard error, you will further shift it to this is we call the normal, the standard normal distribution, which means the mean is 0. This the variance of it is 1, right? So this is how I memorize this theorem. You just take the mean of the sample. So the central limit theorem you can think about is the theorem of the sample mean. It's not about the theorem about x. It's the theorem about the x bar. The x bar means the sample mean. And when you think about this way, and you can use this graph to memorize this theorem, right? So you first write down this formula. The x bar, it has the distribution, it's normal distribution. It have a mean of mu and variance of sigma squared divided by n. And you can rewrite this formula to shift it to a standard normal distribution. So this is what we call the central limit theorem. Okay. Since it's very important, I just double check if everyone already know this theorem? If you have any question, just feel free to unmute and ask at this time, and then we'll stop. Okay, so I think everyone already know the central limit theorem. So let's do a quick exercise. So here we just applied the CLT. The CLT is the central limit theorem for an exponential distribution. So recall you learned from the previous course that the exponential distribution can write down as this formula, right? So how does CLT apply on the exponential distribution data? So can you write down the formula like this, right? The formula like this is that how do you calculate the mu and the sigma square and write down the formula like this? That means how does CLT apply the exponential distribution data? Your solution will look like this one, right? You just replace the mu and sigma square. So that problem should be how do you calculate the mean of the exponential distribution and the variance of the distribution exponential distribution. Okay, so let's do a quick exercise, and I will send out the breakout Zoom. So to calculate the mean and the variance for an exponential distribution is not very easy, right? So you can think about the definition of how do you calculate the expectation and the variance, and then you apply the CLT and you will get the results. This is the basic idea. Okay, so I will send you to the breakout Zooms.
Perdón.
Está bien.
Hi, Shishi.
Hi, everyone. Have you guys have come out the solution?
Something like that.
Is anything goes well so far?
Yes.
Okay,
Yeah, yes.
great. Yeah. I will switch to another room. So see you later.
Great.
Okay.
Y lo mismo pasa con la varianza.
No, porque vos tenés que o sea, la varianza de la media es la varianza, abrís paréntesis y tenés todos los valores de la varianza sobre n.
Sí.
¿Tá?
Claro.
Cuando vos haces eso, la n la pasás para afuera y te queda 1 sobre n al cuadrado.
Claro, 1 sobre n cuadrado. Sí.
Para un poquito. Entonces vos tenés 1 sobre n al cuadrado por la varianza de todas esas cosas que estás sumando. Que como son independientes, haces la varianza de cada una.
Sí.
Entonces te queda 1 sobre n al cuadrado, abrís paréntesis, por la varianza de esta más la varianza de... Entonces es 1 sobre...
Okay, cool. So is everything goes well? Have you guys like come up the right solution? Okay, so let us I will share my screen now and we will like go through this question again. Okay. Okay, so here is the basic solution. So let's divide it by step. Okay, so for so to calculate the expectation for exponential distribution, like I said, right? This is the formal mathematical definition of what we call the expectation. You multiply it by the x and divide it by its probability, which is the PDF at this times, right? And you integrate those values, and you will get this one. And here is a little bit tricky because not everyone remember how to calculate the integration actually, but I really suggest you to open your calculus books and refer to your calculus books and to to see how to integrate by parts, because this is very useful for your exam, both your exam and exercise. So double check, make sure that you know this, how to do the integration. If I think most of you don't remember, I can use the next recitation to talk about some calculus tricks. But I really hope that you double check to make sure you know how to calculate this integration. Okay. So this is the integration by parts, which means you make one part constant and integration the next part, like this one. This is the trick from the, you should see it from your calculus class. And here you get its result. It's just about calculus when you do it step by step. So I think the most idea is you know how to calculate the expectation. This is the formal definition. You will use it multiple times in our course. That is, first you have its value, and you have its associate PDF or PMF. That is the probability, right? And you do an integration. That is pretty much the same for when you calculate the variance. I suggest you write down at this, look like this, because you don't directly calculate the variance, but you calculate the expectation of the x squared, right? This is also the definition. By definition, you just replace the x to be the x squared. So how do you calculate the expectation of n squared? You just replace here to the x to the n. It's pretty simple, but this is just, you do the integration. This is all math. And then you calculate like this. So due to the time limits today, so I won't do step by step. I just show you the basic idea, but this is all integration. It's more mathematics. You do like here, and this is by the EX square, right? You just get the square of the EX. And here, this one, I would say that this is really important. This is, I think, is the conclusion from your probability course. That is, when you calculate the variance of X, you should just, first you calculate the expectation of X squared and minus the square of the expectation. So you will then get the variance. So I really suggest you follow this workflow when you do the CLT, or in the future work, when you calculate the expectation and variance. You should not directly calculate the variance, right? You should first calculate the expectation of X squared and also the expectation square. And then you subtract two stuff, and you will get your variance. And this is the variance. So make sure that this is not the standard deviation. The standard deviation is the square root of the variance. That is the square root of 1 over sigma squared. This is called the standard error. This is the variance. Okay, so for this course, I highly recommend that for those common distribution, like the exponential distribution, normal distribution, you should already familiar with what is the expectation of this common distribution. Like if I said binomial distribution, right? You should remember its variance should be NP, and variance is NP 1 minus P. So you should familiar and remember. I highly recommend when you do exam and your exercise, you can find those solutions on the Wikipedia, or you just Google it. But I highly recommend you to do it on your own at the first time. But then you should memorize those solutions, because this solution is the exponential distribution is a very common distribution, right? You should memorize those conclusions. That is, the mean is 1 minus lambda. The variance is also my 1 over lambda square. And then at last you applied the CLT, right? You just replace the mu and the sigma square, but I should remember that you should divide it by n. And then here we will get the results. Okay, so this is the first recitation. Yeah, so sorry for my the room technical issue today, but I think this is all stuff today. We go through random variables, law of large numbers, and central limit theorem. So if you have any suggestion, I think due to the time limit, I have another session to go. So if you have any suggestion, like if you think our recitation is too easy or is too complicated, feel free to ask Cecilia, and she will gather your suggestion to me. I think we are improving our recitation next time, and hopefully to see you guys, all of you guys next time, and we will talking about more probability topics and review more concept next week. Okay, see you next time.
Remember that
Okay,
on
thank you.
Friday are office hours.
Okay,
Say
thank you.
6 p.m.
Okay.
We'll be there.
Good night.
Okay.
Yeah.
Bye bye.
Bye-bye.
Good night.
Thanks.
Bye bye, everyone.
Bye.
Ciao.
Yeah.
Bye bye.
Bye bye.
Thank you, Zujie.
Yeah, it's fine.
Bye.
Yeah, I will move to the next session. Yeah.
Yes. Okay.
Okay.
Bye, Cecilia.
Bye bye, Karen.
Cecilia.
Bye, Zishi.
Yeah.
Bye.
Bye bye. Have a good night.